Assalamualaikum and good evening. My name is Muhammad Amirfan bin Hasbi Allah. Today I will present M12, which is IIR Filter Design. I will present the introduction of this slide. Filtering is process of changing signal's spectral content. The change is usually to attenuate a range of frequencies in the signal while allowing the other frequency to pass through. How does that transform and discrete time Fourier transform used to design the filter? First, for example, filter IIR, which is the technique used is bilinear transformation. The Z transform is used to convert an analog filter to the digital filter, and then to obtain the different equation. And in discrete time Fourier transform, it used to analyze the spectral response. And then this is example of types of ideal filter. This is high pass filter, which is the only parameter used is cutoff frequency, which is omega c. High pass filter, low pass filter, pass band filter, and band stop filter. High pass filter is for omega c to pi is 1. Low pass filter from 0 to omega c is 1. Pass band filter, there is 2 omega c, which is omega c1 and omega c2. Will only produce 1. And band stop filter from 0 to omega c1 is 1, and omega c2 to pi is 1. Okay, that's all from me. Thank you.
My name is Dizul Hadi and I will continue on our presentation on the non-ideal filter. Okay, so for ideal filter, we notice that the graph is flat, but however for non-ideal filter there is a ripple shown in this figure. Okay, so for a non-ideal filter, we have a pass band ripple and also a stop band ripple, and the magnitude is notation is delta P and also delta S. And for the frequency of pass band and also frequency of stop band is also shown here. And this is important when we want to know the characteristic of the filter. And also the filter also have the transition band, which is the difference between the pass band frequency and also the stop band frequency. And for the filter order, we shown the symbol as N, a big N. Okay. As for designing a non-ideal filter, there are two ways. The first one is the bilinear transformation, and the second one is the impulse invariance. The one that we focus on is the bilinear transformation. Basically, the techniques involved are more towards converting the system from the continuous time, which is notated in (s), towards a discrete time system function, which is notated as a (hz). So in other words, we are changing the s in the system of continuous time to a z, which is in the discrete time function. Okay. So in a bilinear transformation, we will use this equation where we transform the s into c, which c with 1 minus z to the power of -1 over 1 plus z to the power of -1, where the omega, which is, we call this as a analog frequency, will be shown with this equation, which is c times with tan of omega over 2. Okay. We should also be noted that c is equal to 2 over ts, which is ts is the sampling time, and this shows the relationship between the continuous time frequency and also the discrete time frequency. So now we will continue on the designing procedure of the filter. The first part, we have to determine the characteristic of the filter. Usually this is given by the question or criteria, and the characteristic are the delta P, the delta S, the omega P, omega S, omega C, and also the N, which is the order. This is important because we want to know the characteristic of the filter, and then only after that we can design the filter. So after we have found the characteristic, either one that can be continued on, we will have to find the HS, which is the transient, which is the response, and also the analog omega C, and also the N. But if you already found it before, we don't need to find it again. Okay. After we have find the response, we transform it to Z plane, which is from HS, the original one, to the HZ. And after we obtain the HZ, we obtain the time domain representation of the system to be implemented on our question or design. That's all.
Okay, Assalamualaikum. My name is Abdurrahman bin Muhammad Amin. So my part is I will describe about filter that is used in the IIR filter design. Basically, there are three types of filter, which is Butterworth, Chebyshev, Bessel. But in our topic, we only cover Butterworth filter. Under this filter, there is one important formula, which is Hj omega square is equal to 1 over 1 plus omega over omega c in the power of 2n. Omega is represent analog frequency, omega c represent analog cut off frequency, and n represent filter order. There is one special case under this filter, which is if there is omega c is equal to 1, we can refer to the table provided. For more understanding, let's go to the example. Okay, hi, we continue again with our example. Okay, these are the question for example 1. Okay, for step 1, we specify the filter characteristic, which is omega c equal to 0.5 pi and n is equal to 2. Since in the question it doesn't provide omega c, we can assume that omega c is equal to 1. And since omega c is equal to 1, we can use the table provided for the order 2, and we choose the equation Hs is equal to 1 over s squared plus 1.4142s plus 1. After that, we transform the Hs into the Hz. To transform into the Hz, we use the formula Hs equal to C in the bracket of 1 minus Z to the power of negative 1 over 1 plus Z to the power of negative 1. Since we don't have the C value, we use the formula of omega C equal to C tan omega C over 2. After that, we insert the value of omega C, and then we get C is equal to 1. After that, we insert the value of C that we get into the formula of S, and we get the formula of S is equal to 1 minus Z to the power of negative 1 over 1 plus Z to the power of negative 1. After that, we insert the equation of S that we get into the previous HS equation. And after we simplify the HS equation, we will get the Hz equal to 0.2929 over 1 plus 2z to the power of -1 plus z to the power of -2 over 1 plus 0.164 z to the power of -2. And lastly, we get the different equation from the previous Hz, which is yn equal to 0.2929 in the bracket of xn plus 2x n minus 1 plus x n minus 2 minus 0.16 y n minus 2. Okay, that's all for example 1.
Assalamualaikum, my name is Muhammad Mumtaza, and now I will explain example number 2. So, for this example, it is a bit different from the previous example. This is because, for this example, we do not know the number of order of the filter. So, first, we have to decide. As my friend said earlier, there are 4 steps. So, first of all, we must check the characteristics. So, as you can see from the upper half, the information given in the question. So, delta S equals to delta P equals to 0.1. So, this part is shown in the rippling part of the signal. Next, we have omega P and omega S, but only for the digital values. We don't have the analog values. So, we must find that value in order to get the order of the filter. So, for the second part, we draw the filter or the signal so that we can see how the signal goes. Okay, next up, so because we don't have the analog frequency, so we can set it or assume equals to 1. So, and then we can use the data information before to get the analog signal for stop band and pass band. So we can use this formula like my friend said earlier, and after we put in the information, we will get 0.7265 and also 0.3249. Okay. After that, we use the magnitude squared spectrum and we put in the value that we just found, and also not to forget the analog cut-off frequency. So we will have these 2 equations. Now I am going to explain on the 0.9 and 0.1. So, like in the graph earlier, we can see that the delta S and delta P is 0.1. So, for the magnitude, we cannot take a value more than 1 because 1 is the maximum. So, what we do is we take 1 minus 0.1 and also 0.1. 1 is up here and also the other one is down here. So, when we put in an equation, we have 2 equations, equation 1 and equation 2. And then, after we manipulate and rearrange, we will get a value around 3.7569. So, as you can see, this is the filter or the order of the filter. But for the order of the filter, we must take a round number. So, we round off to 4. So now we already have the order of the filter. Okay. Next, we have the third step, which is when we have the equation from table 7, we have to change it into Z transform. But first, remember, in order to use table 7, our analog cutoff frequency must be 1. And this is true because we assume it is 1. Okay, now we can change into Z transform by substituting S equals to C in the bracket 1 minus Z power of negative 1 over 1 plus Z power of negative 1 inside the HS equation, where C is actually 2 over TS. But remember, we have this first equation, so we can just input the order of the filter, which is 4, inside this equation, and we can get C. So finally, we arrive at the final step, which is the fourth step. So in this fourth step, we must complete it or make it in a time domain form. So it can be in two types or either one. So it is either with an impulse response or a difference equation. The answer will be shown right after this.
Assalamualaikum. My name is Ahmad Aiman bin Aziz. So now I will explain on my part, which is the pair of poles solution. As in example 2 that my friend has explained before, there are two pairs of poles, which is n equal to 4 or order 4, fourth order. Thus, the denominator for the Hz is presented by multiplication of two sets of second order expressions. So for each pair of poles, the transformation of Hs to Hz using bilinear transformation, when we assume that omega c analog is equal to 1. So Hs is equal to this, and after we bilinear transformation, it will become Hz equal to this. So from the table we can also have this formula, where these three formula will be used for when n is equal to even. So what I have taught before is when n is even. However, when n is odd, there will be one extra poles after pairing all of the conjugation poles. Thus, the bilinear transformation from Hs, this Hs will become Hz. And from the table we also have this formula, which is D1 and D2. So now, to be able to understand more on this, we will try to do example 3. For example 3, we need to do the bilinear transformation for the fourth order Butterworth filter. So for this question, we assume that C is equal to 1. So from the table, we get for the fourth order, we use the formula Hs equal to this, and after we do the bilinear transformation, it will become Hz equal to this. So again, from the table, we will have to find the value of B1, B2, B3, D1, D2 and D3 by using the value of pole A and the value of C that we have assumed before. So finally, after we substitute we get all the value of B1 until B3 and D1 until D3, we substitute all the value into the formula of Hz, which is this, and finally we'll get the answer, which is Hz equal to this. So that's all. Thank you.